Hello everyone, now let's look at problem number 6 of the 2024 free response problem. This is asking us, and this is gauging our level of understanding for kinetics and Lewis structure and valence shell electron pair repulsion theory. And this is very important because this one is part of a free response problem for 2024 exam, AP exam, but usually it can be easily transferred into multiple choice problems. So then let's have a complete understanding of the kinetics and also combination of Lewis structure and valence electron pair repulsion theory for shape and geometry of the molecule. First, we are given a decomposition reaction, 2 moles of nitrogen dioxide gas at high temperature, 546 degrees temperature. Usually this type of gas phase reaction is requiring the presence of catalyst. The catalyst is not mentioned here, but assume always the catalyst is there, and it is decomposing into 2 moles of nitrogen monoxide gas and oxygen gas. And so for 100 seconds, for the initial 100 seconds, the concentration of the reactants, nitrogen monoxide gas concentration, was monitored, and it is translated into a logarithmic scale and inverse scale versus time, and 2 graphs are shown right there, and it is asking us to interpret it. The rate was determined as second order with respect to the nitrogen dioxide. Explain how the graphs indicate the reaction is second order with respect to nitrogen dioxide. First, let's look at the rate. And the second order, this one, definitely the order is not linear. This is non-linear. This is curved, definitely curved. And let's look at our inverse of nitrogen dioxide per with respect to temperature. So this is linear. Okay. And what is this? How can we interpret this reaction? The rate of disappearance of nitrogen dioxide per time and instantaneous change can be written as T concentration over Tt. Because it is reactant, we can write negative right there. And this can be first order with respect to nitrogen dioxide or second order square. And this is a differential equation, and we are not asking you to solve this differential equation, but understand the result is a result of solving this differential equation. When you solve this first order differential equation, we are ending up with logarithmic of concentration, ln NO2 concentration at certain time t is ln n sub 0. I mean ln concentration at certain initial temperature, initial concentration minus kT. So then if this is linear, the slope will be negative k. So it is decreasing always. Makes sense because as time goes on, the reactant will be consumed. It will be decreasing in concentration. In second order reaction, when you solve it, we are ending up with inverse of the concentration, NO2 concentration at certain time t is equal to 1 over the initial concentration. Let me write it as sub 0 and plus, this one is plus kT. Plus kT. Okay. So in this case, the slope of the reaction, slope is k. So this one is slope with respect to time, slope. Simply it is y equals mx plus b form, and 1 over n sub the constant 0, this is the y-intercept. So this value is y-intercept is 1 over the concentration of NO2 0 right there. And because the first one is obviously it's not linear, initially it was very rapid change, and then when you connect 2 points, the slope is decreasing, so it is slowing down as temperature goes on. So this is typical. This is not definitely not first order reaction, but the second one, when you draw the graph of reciprocal of the concentration of reactants over time, it is definitely linear, which is an evidence that this is a second order reaction. Now, at a certain point, the rate of disappearance of nitrogen dioxide is a given right there. Determine the rate of appearance in molarity per second of oxygen gas at this point. And remember, because the ratio is different, 2 moles consumed and 2 moles and 1 mole of oxygen gas generated, and their rate of disappearance, rate of appearance all different. So we need to write unique reaction ratio, a unique reaction rate. In case of the reactants, we are writing negative. So then change in concentration per time is equal to change of the product over time. And this is again change of the product over time. But they are not same. 2 moles of nitrogen dioxide decomposed to produce 2 moles of nitrogen monoxide, but 1 mole of oxygen is generated. So to make them equal, we need to divide by their coefficients, 1 over 2, 1 over 2, and in this case it is simply 1. So we are looking at this relationship. This is given, and it is asking, this is unknown. This is unknown. Appearance of the oxygen gas, rate of appearance per time, and then the rate of disappearance, multiplied by negative half. And we know that rate of disappearance, this one, over time, disappearance negative there, it is 6.52 times 10 to the negative 7 molarity per second. In 1 second, 6.57 times 10 to the negative 7, which is, let's say, this is 652 nanomolarity. This one is disappearing. And this one, the appearance rate is half of it, okay? Half of the disappearance rate. So then this one is 6.52 times 10 to negative 7 molarity per second, half, which is 3.26 times 10 to negative 7 molarity per second. So this problem is asking us, do you understand how to calculate the unique reaction rate and how to interpret the disappearance and appearance rate? Because the disappearance delta of concentration is always negative, so we put negative there always to make it positive. All right, now let's get the next problem. It is asking us about draw the Lewis structure of this polyatomic ion, nitrogen dioxide cation, and nitrogen dioxide. Let me write nitrogen dioxide has 1 nitrogen and 2 of oxygen. And nitrogen belongs to group 5A. It has 5 valence electrons. Oxygen has group 6A, 2 valence electrons. Total 17 valence electrons. It is odd number of valence electrons. That's why we cannot have a good Lewis structure of nitrogen dioxide. We need to apply the molecular orbital system, orbital theory, to have really good understanding of nitrogen dioxide. Okay, then it's asking us to draw the structure of nitrogen dioxide. So, nitrogen dioxide cation. So this one is 17 minus 1. It has lost 1 electron. So total 16 valence electrons available. So then nitrogen, oxygen right there symmetrically and connect them with a single bond. So total single bond is composed of 1 pair of electrons, 2 electrons. So far we have used 4 electrons. And then let's satisfy the terminal atoms first with octet, putting 3 lone pairs each. And I use 16 all. I don't have any more electrons. And then finally, any more valence electron left. Finally, satisfy the first one into an octet. In order to do that, we need to move the non-bonding lone pair electron to the bonding region, making to bonding. And finally, good Lewis structure would be making them into double bond like here, double bond like here. Now an oxygen has two lone pairs. In this way, now all of them satisfy the octet condition. So this is a stable, good Lewis structure. And also, another way is you can make single bond of oxygen, 3 lone pairs in this way, and triple bond with oxygen. This will be one of the resonance structures. But when you assign the formal charge, I mean, let me erase this one. This has only one lone pair. So in this case, when you assign formal charge, oxygen has +1, this is -1, nitrogen always +1. So this is very unstable. So the major stable, the Lewis structure will be double bonding right there, double bonding right there. Put 2 lone pairs right there. Okay, and let's go to the next one. Claim the bond angles in nitrogen dioxide and nitrogen dioxide, this cation has different bond angle. Do you agree? Okay, let's draw those structures. The first one has a radical in nitrogen, and this one is occupying unhybridized p orbital. This is sp2 hybridized nitrogen, and then the radical is occupying unhybridized p orbital. Let me draw this one. This is unhybridized p orbital. So this is sp2, and the structure is trigonal planar. The bond angle will be close to planar. Let me erase it, write it again, planar. Bond angle will be little bit, this bond angle will be like 120 degrees and smaller than, around 120 degrees. We don't need to know the exact value. But in the case of nitrogen dioxide cation, it is only 2 of them around the central atom. So it will be, this nitrogen is sp. This is sp hybridized. Only two of the bonding available. It will be 180 degrees apart. It is linear structure, linear. So then definitely the bond angle is different, and I completely agree with this claim. All right, in this problem we are looking at the kinetics, and this is a combination of kinetics and the Lewis structure, and I see that it can be easily converted into a multiple choice problem. And so let's see A and B very well to determine if a reaction is, what is the criteria for determining the reaction order, first order, second order, when we are rearranging the data and draw the data into logarithmic scale or the inverse scale as a function of temperature, and then also the Lewis structure and applying the hybridization and valential electron pair repulsion theory to determine the shape and bond angle. Okay, everyone, thank you for watching this video, and I'll see you in next video.